So we have a privilege here to introduce Dr. Harsha Hutridurga from IIT Bombay. Let me just give a very short and brief introduction of Dr. Harsha. He's an associate professor in the Indian Institute of Technology, Bombay right now, and he has completed his degrees from TFIR and École Polytechnique, France. He has done a postdoctoral from Imperial College London and University of Cambridge. The research interests of Dr. Harsha includes theory of homogenization, mathematical statistical mechanics, metamaterials, numerical analysis, and a lot more. So it's a privilege for us to introduce Dr. Harsha, and now I will stop the sharing of my screen. And today he will be talking about the topic entropy method, which is a tool for studying the reaction-diffusion equation. Welcome, Dr. Harsha, and now over to you.
So thank you. Thanks very much for this opportunity to present this work. I will give a brief introduction to this method known as the entropy method. Okay? And the equations that we would like to study are the reaction-diffusion systems. So whatever I present today, it's joint work with Soumijit Das, who is a student here at IIT Bombay. So this talk is about last time behavior of solutions to reaction-diffusion systems. Okay. So the setting is as follows. We will discuss everything in 3 dimensions now, 3-dimensional spatial domain, omega. And we have got m's number of species. M is just the number of species that are involved. They are involved in one single chemical reaction, a reversible chemical reaction like this, where these alpha i's and beta i's are known as the stoichiometric coefficients. They are just some non-negative real numbers. So it essentially tells you that alpha 1 amount of y1 and alpha 2 amount of y2 and alpha m amount of ym, they are coming together to get into some reaction, and they yield this beta 1 amount of y1 and so on and so forth. Okay. Now, if you denote the concentration of the species yi by a sub I, which is a function of x and t variables. So x is a point in space and t denotes time here. So ai denotes the concentration of the species yi. By that, I mean, like if you take any subdomain of omega, you integrate out this ai in that subdomain, it essentially gives you the amount of that species present in that subdomain of omega. That's how these concentrations need to be understood at a given time t. Now, when it comes to modeling this reaction diffusion equation, so this is what you end up with. So you have got diffusion equation here for ai, and these little di's are the diffusion coefficients. We are assuming that they are non-negative. And this right-hand side here, this is known as the rate function. So this can comes out of something known as the law of mass action for a given reversible chemistry. So we'll just admit that it has got this particular structure. So it has got this polynomial structure in AIs, and for each of these, there are m such equations because there are m's a1 going on up to am. These are the unknowns. Okay. So d1 going on up to dm. These are the non-negative constants, which are known as the diffusion coefficients of corresponding to the species yi. Okay. We are mostly interested in the case when they are not equal to one another. Okay, when they are equal to each other, somehow the analysis is way simpler. So we will assume that they are distinct. So we are studying concentrations here. So we are going to assume that we are feeding. This is an evolution equation. So you will feed non-negative initial data for this equation. And we are also assuming that, in this bounded domain omega, on the boundary of your domain, there is no outward flux of your concentration. So this is the Neumann boundary condition for AIs that is equal to 0. So this is the setting. So we will work with a reaction diffusion system and with initial data and homogeneous Neumann boundary condition. Okay. So rather than working with this, very general reaction diffusion system, we will be working with a particular case of a three species model. Here we are considering 3 species, A, B, and C, and they are undergoing this particular kind of reaction, A plus B they react to give C, and C disintegrates to give back A plus C. So A plus B. So that's the chemical reaction that we are interested in. And rather than using those notations AIs, we will use little a, little b, and little c for the concentration of capital A, B, C. And if you write down that rate function that I had written down for, you see here, alpha 1 is 1, alpha 2 is 1, and beta 1 is 1. Okay, so if you use that particular notation there, beta 3 is 1, so beta 1, beta 2 is 0. So if you go back to this expression which was here, if you write down this expression for the rate function, you will see that it takes this simpler looking structure for this particular reaction. So the equation for A, B, and C. Please observe that the right-hand sides for A and B, they are alike, because somehow we don't distinguish between A and B. They are on the same side of your chemical reaction. And for the equation for C, it just changes the sign. Okay? Now, we admit this theorem, which was proved some years ago. It says that, okay, if you take this reaction diffusion system, this particular one, you feed it with initial data which is non-negative, and you have to give 3 functions. So if you give C2 functions as initial data to this problem, then you also assume that at least one of these diffusions constants are strictly positive, so that you are not working in the degenerate case of an ODE system, so that at least there is one partial differential equation in this system. So you assume that at least one of them is strictly positive. Then there exists a unique non-negative solution to this reaction diffusion system, and that is also smooth. So it is C2 in both time and space, each of these, A, B, and C. So we will admit this result that there is a very nice solution to this problem once you feed it an initial data which is non-negative and smooth. Okay. The first observation, this is a very simple observation that we can make here, looking at the system of equations that we have written here. So as I commented earlier, if you look at the right-hand sides for the equation for A and C, see, they just differ by sign. So if we were to add these 2 equations, the equation for A and equation for C, the reaction terms, they vanish, they go away, they cancel each other. So you'll be just left with an equation for A and C added. Okay. And then when you have added these 2 equations and you integrate in the x variable, using the fact that there is homogeneous Neumann boundary condition for A and C, your Laplacian terms, after you have done an integration by parts in the x variable, they do not contribute. And so you are left with this. This is a conservation which is happening, which tells you that the sum of these concentrations A and C, when you integrate in the x variable, they keep the same value for every time t. And what is that value? That is equal to the initial sum when integrated in the x variable, whatever that number is. Okay, so this is a number, and you simply call it m1 times the measure of omega. We are always working in bounded domain, so this is finite. Okay, so you can always factor m1 like this. So m1, if you want to think about it, is just the average of the sum of a0 and c0. Okay, so m1 is well defined once you give me what is a0 and c0. Okay. Similarly, if you add the equation for B and C, you will find that the sum B plus C is again conserved when you integrate in the x variable for every time t. And now the average of B0 plus C0, you call it m2, okay, over the domain omega. So let us just keep these 2 constants in mind, m1 and m2. They will be used very frequently in the remaining part of this talk. So there are, once you give me the initial concentrations A0, B0, and C0, I can uniquely define these 2 constants m1 and m2. They are well defined. Okay? And in fact, the diffusion constants being non-negative is good enough here. In fact, even if they vanish, these conservation properties are still true. So now, this is what we are interested in. This has some kind of relation to what we saw in the previous lecture, we are interested in the last time behavior of the solution to this system. So we have got this solution A, B, C. We want to know what is the behavior of this solution to this problem when t becomes larger and larger. Okay. So we will first write down the, what does the equilibrium state has to satisfy. So blindly speaking, you can just drop the time derivative terms and you look for solutions to this system here. Okay, so we are trying to find A infinity, B infinity, and C infinity, which solves this system of equations. Okay, this is an elliptic system, non-linear elliptic system. Okay. Now observe here that if I take constants C infinity, A infinity, B infinity, such that C infinity equals A infinity times B infinity. See, the point I'm trying to make is, let us work with constants here. So we will take three constants, A infinity, B infinity, and C infinity, such that C infinity is just the product of the other two. If we do that, the right-hand side in each of these equations, it vanishes, and also the left-hand side vanishes. So essentially, you have found a solution to this system. Okay, a solution. We are not claiming that this is the only solution to this system. You have found a solution. Now, because there is conservation at every time t, you expect the conservation that a plus b, a plus c being integrated in x, keeping the same value, okay, equals to m1 times the measure of omega. You expect the same kind of constant, conservation property to hold even at the equilibrium state. So that essentially tells you that a infinity plus c infinity now integrated over omega and divided by the measure of omega should be equal to m1, right? And the same thing for b infinity and c infinity. So you got these three relations between c infinity, a infinity, and b infinity. m1 and m2 are decided by your initial data, as I remarked earlier. So now, if you substitute for c infinity equals to m1 minus a, or a infinity is equal to m1 minus c infinity here, and b infinity is equal to m2 minus c infinity here, you will get a quadratic equation for c infinity. Okay, and then you can solve that. You'll get two roots for that quadratic equation, and you will pick only the one root, which will make sure that all a infinity, b infinity, c infinity are non-negative, and that c infinity is this, okay, which is given again in terms of these two constants m1 and m2 decided by your initial data a0, b0, and c0. Okay, and once you have found c infinity, you can go back to these two relations and write down what is a infinity and b infinity. Okay, so the story so far is that we have got a 3x3 reaction diffusion system, and we have identified a homogeneous equilibrium state. By homogeneous, I mean that these are constants. Okay, so we have identified a homogeneous equilibrium state for that reaction diffusion system, and we can actually compute it explicitly, which is given in terms of the initial data. So once you have fed your reaction diffusion system with an initial data a0, b0, and c0, using a0, b0, and c0, you find these constants m1 and m2. And using m1 and m2, you find c infinity, a infinity, and b infinity. Okay, I hope that is clear. So now we ask the following question. Like, once you have fixed your initial data for your evolution problem, this 3x3 system, will the solution A, B, C to that, the unique solution that you have, will it converge to this homogeneous equilibrium state? Okay, and in fact, this particular question was answered for this 3x3 system by Laurent de Villette and Clemens Fellner back in 2006, and their theorem goes as follows. They say that, okay, this is a very important assumption that I want you to keep in mind. They are assuming that all the diffusion coefficients, dA, dB, and dC, they are strictly positive in your reaction diffusion system. And you take your initial data A0, B0, and C0 such that you got M1 and M2, which are strictly positive. Then the result is the following. They said that this A, the solution to your 3x3 system, one of them, A converges to A infinity, that constant which we determined earlier, in the L1 norm, and that convergence is exponentially fast. You see, this is exponentially fast in time. And the value of this theorem, in some sense, is you see these constants which are sitting here, this k and lambda, they're very explicit. You can, in principle, compute these constants. Okay, they're determined by the initial data that you give, okay, which essentially determine what M1 and M2 are. And also they are dependent on the strictly positive diffusion coefficients, which are there in the reaction diffusion system. Okay? So this is the result. It tells you that for a strictly positive strictly positive diffusion coefficient, and for any given initial data, your solution converges to these equilibrium states A infinity, B infinity, C infinity in the L1 now. Okay? And the convergence is exponentially fast in time. So the idea of the proof of Degenerate and Fellner is to go via Lyapunov functional. Okay? And the method that they used goes under the name of the method of entropy, and that's what we will try to understand. So what they did is, okay, associated with this three functions A, B, C, you define a functional E. This functional E is essentially given here. It's the integral of A log A minus A integrated in the X variable. Similarly, B log B minus B and C log C minus C. Okay, you got this expression for the functional E. What you do is you take the solution ABC to your 3x3 reaction diffusion system, and you compute this functional E for that solution. You differentiate in time this functional. So you blindly take the derivative inside the integral in the X variable. So when you differentiate A log A minus A, you get natural log of A times the time derivative of A. So that you can check. Similarly, these terms involving B and C. Okay. Now, at some stage in the entropy method, when you are introducing this Lyapunov function, you have to use the fact that A, B, C are solving your 3x3 system. So now you have got this time derivative of A, you substitute for the time derivative of A, okay, from your equation, which tells you that it is equal to the Laplacian of A times the diffusion coefficient plus C minus AB, the reaction term. Similarly, the terms for the time derivative of B and time derivative of C. Okay. Now, what you do next is simply regroup. You see, there is natural log of A times C minus AB, and you can factor C minus AB from each one of these terms, and a nice structure comes along. And wherever there is a Laplacian, you do an integration by parts. Okay. When you do an integration by parts, when the gradient hits the natural log of A, you get 1 upon A times the gradient of A. Okay. So you get this term. This is the expression that you get when you have done the integration by parts in the Laplacian term. Of course, the integration by parts will throw you a negative term as well. Okay, a negative sign. And the regrouping for the reaction term, as I was telling, it can be regrouped to give this expression. And you see, this term involving the natural log, it is also strictly positive because AB minus C times natural log of AB minus natural log of C is a positive quantity, and there is a negative sign next to that. The point to be noticed here is that each of these terms are negative here. Okay, they are at least non-positive. So you get that this is just the finite sum of non-positive terms. You get non-positivity here. Okay, so you have shown that this E, this functional that you defined, is indeed a Lyapunov functional for this evolution system. Okay, the d by dt of E of ABC has got a sign now. Okay? Now, this right-hand side, which was here, with a negative sign next to it, we will give a name to this. We will call this entropy dissipation, and we have just gathered that term. Okay, we called it D of ABC, and we have given this expression here. And we have not written the minus sign next to each of these terms. That's okay. The entropy dissipation functional, this is called. Now, we will just rewrite these terms involving the gradients. We have got gradient of A whole square divided by A. That can be rewritten as gradient of square root of A whole squared. Okay, and of course that throws in a 1 upon 4, so we multiplied by 4 here, each of these terms. Okay, going from this equality to this equality is just a rewrite of these gradient terms. Okay, to run. And we are working with only non-negative solutions to your problem, the 3x3 system. So the taking square roots is allowed. Okay, so you get this. Now you got this thing, and what have we just shown? We have shown that. We have shown that if ABC solves the 3x3 reaction diffusion system, the time derivative of this entropy functional evaluated along the solution to this problem is just negative of this dissipation, entropy dissipation function. Okay, this is what we have shown so far. Now, what did Laurent Degenerate and Clemens Fellner do in 2006? They said, okay, they are going to relate this entropy dissipation D with something known as the relative entropy. Okay. So for that, the theorem goes as follows. So you take any two strictly positive constants, m1 and m2. Okay. Now, once you give me two constants, m1 and m2, I can blindly build this a infinity, b infinity, and c infinity with the formulas, the solution to the quadratic equation that we wrote down earlier. So you can build these three constants, a infinity, b infinity, and c infinity. Now, this theorem, this lemma here, it tells you that you take any bounded, it's very important, bounded non-negative functions on omega, a, b, c. They need not be the solutions to this 3x3 system that we are working with. You take any bounded non-negative functions on omega, a, b, c, such that a plus c when integrated in the x variable is actually equal to m1 times the measure of omega. So essentially, we are telling that the average of a plus c is equal to m1, that constant that you have fixed, and the average of b plus c is equal to m2. So you take any three functions, bounded functions, which have this property. Okay. Then they proved that this dissipation, because you can always define d of a, b, c for nice functions a, b, and c, because for any non-negative functions you can, which are smooth enough to define the gradients and all. So DABC is defined. They proved this general inequality. This is a functional inequality, which is true for certain class of functions. DABC is greater than or equal to some constant lambda times this difference, this entropy functional evaluated at ABC minus the entropy functional evaluated at these three constants, a infinity, b infinity, and c infinity, determined by m1 and m2. Okay, and this difference is referred to as the relative entropy. Okay, and they also showed that this constant lambda, which is sitting in this inequality, it can be explicitly given in principle, at least, in terms of dA, dB, dC, the diffusion coefficients, which are sitting in the expression of the dissipation functional d, and these two constants m1 and m2 that you have fixed, omega and L. L is the maximum, the L infinity bound that you have for these three functions that you are taking. Okay. Now, the key point that I would like to emphasize here, that this result that you see here has nothing to do with ABC being solutions to this 3x3 system. You give me any bounded non-negative smooth functions, this inequality holds. This result holds. Okay. Now, and in particular, it holds for the 3x3 system that we are working with. So what have we done so far? One observation is that a infinity, b infinity, c infinity, they are constants, right? So when I compute the entropy of these three constant functions, you again get a constant. So when I time differentiate a constant, I get 0. So essentially, earlier we had, if ABC is a solution to the 3x3 system, the time derivative of the entropy is negative of the dissipation, right? That's what we proved by just integration by parts. Now we have simply subtracted 0 from it, nothing more. So we get this. And in the previous slide, we showed this entropy-entropy dissipation inequality, and that holds for the solution ABC as well. It relates the entropy dissipation with the relative entropy. Now, lemma, this is quite clear what's coming next, right? Because time derivative of the relative entropy is negative of dABC. Now, negative of dABC will be bounded from above by negative of lambda times the relative entropy. So now you can blindly apply the Gronwall lemma, which tells you that relative entropy is exponentially decaying in time. Okay, so relative entropy is bounded from above by exponential of minus lambda t times the initial relative entropy that you have. Okay, this is essentially Gronwall lemma application. Now, this is telling you that the solution ABC at any time t, the entropy evaluated at any time t is approaching the entropy at that steady state entropy, and that approach is happening exponentially fast. That's what this little computation shows here. In fact, you can relate this relative entropy back to the familiar L1 norm, and that is related by something known as the Cesar-Kullback-Pinsker inequality, and that I will get back to very soon. Okay, so I hope this is clear. This is the essential idea in the entropy method, that you will have to show that there is a Lyapunov functional, and you will show that d by dt of that Lyapunov functional is minus d of ABC for some dissipation functional, and then you do a functional inequality, which relates the dissipation functional with the relative entropy. And then you apply Gromov lemma, right, to get exponential decay. Now we do, this is the thing that I have summarized here. You have to find an entropy functional in your evolution system. Now you define, once you have found your entropy functional, that kind of helps you define an entropy dissipation function, which is D. And then you have to prove a functional inequality, which has, in essence, nothing to do with the problem that you're working with. So this is a result about functions, so which relates entropy and entropy dissipation. And then that leads to a differential inequality. You will integrate that. That's a fancy way of saying you will use Gromov lemma. And then you have got convergence of relative entropy, and you use some functional inequality again to obtain convergence in LP, which are more familiar. Okay? And if you are interested in knowing more about this entropy method, these are some references, okay, that you can check. So that was the work of Degenerate and Fellner, and we are actually interested in the case when in the 3x3 system that we are looking at, one of the diffusion coefficients vanishes. Okay, so for example, when dB is 0, that means the diffusion equation that you have for B now disintegrates. It just becomes degenerate and it becomes an ODE now. So you got PDs for A and C, and you have got an ODE for B. Okay, and similarly, we have also studied the case when DC is equals to 0, and so now the C satisfies just an ODE. Okay, now we are inspired by these two recent works where they studied this kind of terming of diffusions in reaction diffusion systems and studying the last time behavior for a different set of reaction diffusion systems, and we are doing it for this one. Okay, so now please observe here that A infinity, B infinity, C infinity, all those conservation properties are true even in this case, and the A infinity, B infinity, C infinity that kind of determined by the initial constants A0, B0, and C0 in terms of M1 and M2, that is true even for these degenerate settings as well. So we are interested in knowing what happens to this solution when time becomes larger and larger. Okay, will it converge to the same A infinity, B infinity, and C infinity? Okay. Now, our approach is again entropy method. So we will, what's the first step in the entropy method? You have to give the entropy functional. Okay, so it turns out that you can give the same entropy functional as them. Okay, this is the Boltzmann entropy functional. So this is A log A minus A integrated in X. Similarly for B and C. So that is the entropy functional that we introduced. Now, what did we do next? In the Degenerate and Fellner paper, we differentiated the entropy functional to show that this is actually a Lyapunov functional. So you time differentiate, you get this. So you blindly take the time derivative inside, you get log A times dt of A, and so on and so forth. Now you use the equation. So you substitute for the time derivative of A, and time derivative of B, and time derivative of C. I put something in red here. This is the only change with respect to the Degenerate and Fellner paper, because we don't have diffusion in B anymore. So there is no Laplacian in B. So we have only the reaction term. So you get natural log of B times C minus AB, which this term was also present in the earlier non-degenerate case. Now you do the same thing. Wherever you see the Laplacian, you blindly do integration by parts, and you use the Neumann homogeneous Neumann boundary conditions, and you get the sign here also. You get that this is something negative. So even in the degenerate case where dB is 0, your entropy functional is a Lyapunov functional. So d by dt of E is less than or equal to 0. The only difference with respect to the previous result that we have seen is that this term is missing, the gradient of square root of B, the whole square term, because there was no Laplacian to begin with, so you will not get this term here. Okay. Now, what did we do next? Once we showed that we have found a Lyapunov functional, that means we have shown that d by dt of E is equal to something. That helps us define the dissipation functional D. So that's what we will do now. We will recognize the dissipation functional D. Okay, that turns out to be this one for the degenerate case with dB is equal to 0. Now, we have got this dissipation functional. And we have got this relation that d by dt of E is equal to minus d evaluated at ABC. What is the next step in the entropy method? We have to look for entropy-entropy dissipation inequality, which relates d to some kind of relative entropy, right? The first observation that we need to make is the entropy functional has not changed. We have got the same entropy functional as Develeth and Fellner. Okay. And the equilibrium state has also not changed. The homogeneous equilibrium state is A infinity, B infinity, C infinity, the same exact for the non-degenerate case. The only change is in the dissipation functional D. Okay, and that too, it has got a term missing. Okay, that gradient of square root of B term is missing. So that's the story so far. So now we will give a result about the new dissipation function that we have. Okay, we introduce this notation f bar, which is just the average of any given function f, as long as this integral makes sense. Now you take any, again, the result that we will show in this slide is a general result. Like in the Develeth and Fellner case, that's a functional inequality. Okay, it has nothing to do with something being a solution to some system. So you give me any two positive constants, m1 and m2, and you build this A infinity, B infinity, C infinity using these two constants, m1 and m2. Then this is the result done in collaboration with Saumyajit and myself. So it says the following. Okay, now you give me three non-negative functions, A, B, and C. We have to introduce this. I mean, we will be considering only functions of x and t variables. Here you will see why we are doing this. Anyway, we want to apply it to the reaction diffusion system. So you give me three non-negative functions on omega cross 0 infinity, such that if I sum A and C and integrate in the x variable and average in the x variable over omega, I get m1 for every time t. Okay, and I take B and C and add them and average over omega, and that is equal to m2 for every time t. Somehow we are mimicking that conservation property that the solutions have for the system. And this is the key thing in this result. We also assume that this second function B here, if you compute the L3 half norm in the spatial variable of B, that has a polynomial growth in time. Okay, so it grows like 1 plus t raised to the 5 by 6. Okay, so you give me three functions. There is no growth assumption made on A and C. So only growth assumption on the some LP norm of B is this one. Then we say this. We say that, okay, this dissipation, which we had defined earlier, which can be defined in terms of ABC, so that can be bounded from below by, please observe that this 5 by 6, which is appearing in the numerator, has changed sign here. So you get some lower bound. Unlike the Develeth and Fellner case, we are not showing that DABC is directly related to the relative entropy in this lemma. It tells you that, okay, DABC can be bounded from below by some function of time here, times some terms involving A, B, and C. In fact, square root of A, square root of B, and square root of C. Taking square roots is allowed because we are working with non-negative functions. Okay, so this is there. So let's just keep this in mind that some L2 norms of the square root of A and its average, the difference of those two, is related to the dissipation functional D. Okay, and there is a factor of this polynomial correction is there. Okay. Now, this is not as neat as the Develeth and Fellner case when the non-degenerate case. So we have to relate that lower bound that we have here in this result back to the relative entropy, that E of A, B, C minus E A infinity, B infinity, C infinity. That's what we will do next. Okay, we will bound the relative entropy. So now this is again a generic result, which about functions and not just some functions which are solutions to a differential equation. So you take any three non-negative functions A, B, C, functions of space and time, such that A plus C averages to m1 for every time t, and B plus C averages to m2 for every time t. And furthermore, the L infinity norm in omega t. Omega t is our notation for the parabolic cylinder, that is omega cross 0 t intro. So you take the L infinity norm of each of these three functions that you are working with. That L infinity norm at most grows like 1 plus t raised to some mu, where mu is some positive constant. So if you have got functions which satisfy this property, Then we relate the relative entropy E of ABC minus E of A infinity, B infinity, C infinity back to that fellow that was there before in the previous slide as a lower bound here. Okay, there's an additional term, but this additional term is there. L2 norm of square root of C minus square root of AB squared. But the other three terms are sitting here. And there is also a natural log of 1 plus t corrections. Okay, so this is the result. Now you can club these two things to do something. And this is, I want to emphasize that both these results, which I have shown.
Sorry to interrupt you. Will it be possible to conclude within coming 10 minutes?
Yeah. Thank you. Thanks for that. So both these results that we have shown, they are for functions which satisfy certain conditions. They need not be solutions to this reaction diffusion system. Okay. So now if we put everything together, this D, which is related to some L2 norms of the square root of A and average of square root of A differences, and this relative entropy. So essentially, each of those lemmas that we showed, it had got two conditions, right? So we club all those conditions. So we say that, okay, give me three functions, three non-negative functions A, B, C, such that A plus C averages to M1, B plus C averages to M2 for every time T. And the L infinity norms of A, B, and C are bounded from above by 1 plus t raised to the mu times some constant. And the L3 half norm of B in the spatial variable grows like 1 plus t raised to the phi upon 6. Okay. Then this is the key result that we have shown, which relates the entropy, relative entropy, okay, E A B C minus E A infinity B infinity, C infinity is bounded from above by some, there is some polynomial thing here, 1 plus t raised to that times the dissipation functional t. Okay, and this epsilon, you need not worry about it because there was a natural log correction. That's why this epsilon is coming. The only thing that to keep in mind is, okay, it's not exactly 5 by 6, it's 5 plus epsilon by 6. Okay, so you just wait for long enough, this thing will kick in. That's what we are trying to say. Okay. Now, like Devilath and Fellner did, we can put all of this together. What did we show? I mean, here again, the entropy of A infinity, B infinity, C infinity is constant. So we have just subtracted 0 here. So this is the first step, that E is a Lyapunov functional for our degenerate system. So you get this. Now, and we have shown this by an elaborate way, but under certain conditions, we have shown. Okay. Now, if you club these two things together, you will essentially get to the stage where you can apply Gronwall again. So you have got that the time derivative of the relative entropy is bounded from above by some minus lambda times some, 1 plus t raised to some power times the relative entropy. And again, you apply Gronwall lemma and you show that the relative entropy decays. Now, you please note that the decay is not exponential in time, but this is sub-exponential in time, because this is e to the minus some constant times t raised to the 1 upon 6. So this is sub-exponential decay, okay, in the degenerate case. And I had mentioned a phrase called the Cesar-Kullback-Pinsker inequality, which relates this relative entropy back to the familiar L1 norm. And that is given here. I'll just skip this thing. This tells you that under certain conditions, the relative entropy can be bounded from below by some constant times the L1 norm of these differences. So if you have shown that the relative entropy decays, you have essentially shown, thanks to this result, that the L1 norm of this difference decays. Okay. Now, putting it all together, our main result is this, that if in your degenerate system, dA and dC are strictly positive and dB is equal to 0, now you give the initial condition A0, B0, and C0 such that M1 and M2 are strictly positive. Then A converges to A infinity in the L1 norm, and that convergence is exponential, sub-exponential in time. Okay. Similarly for B and C. Okay. Now, of course, all those relating D to the relative entropy that involved assuming that A, B, and C satisfy certain growth bounds, right, in the time variable. And so we have to essentially prove those bounds hold for our solution for the degenerate case. We have to show that the solution to the degenerate system actually satisfies those two conditions, the L3 half norm of B in the time for every time t can be bounded from above by this, and the L infinity norms are at most like 1 plus t raised to the mu. And I had thought that I can give a brief sketch of that, but I'll just skip it. Okay. And so, in fact, you can do a similar kind of analysis when DC equals to 0. Okay. And you can ask a similar question, okay, whether the solution converges to the equilibrium state, is it exponential or sub-exponential convergence? And we have shown a similar kind of result where the convergence is again in the L1 norm and the decay is sub-exponential in time. And please note that there it was e to the minus t over 1 by 6. Now it's e to the minus t over 2 by 3 in this case. So somehow the decay rate is faster when you turn off DC rather than DB. We are not claiming optimality here, at least the way we have got these decay rates, the rate seems to be faster in this second degenerate case that we have worked with. Okay, and I mean, one can ask, right? Why are you turning off only one diffusion? Can you turn off two diffusions? You can get this reaction diffusion system here. The equilibrium states remain the same, but unfortunately, we are unable to adapt this approach to prove convergence to equilibrium type results for this system. We don't have a result for this. And we have worked with more general triangular systems, and we have studied convergence rates for that. So this world of reaction diffusion systems is very interesting, and there are lots of open questions. In fact, it's a big open question to show that global in time classical solution, a unique classical solution exists for these general reaction diffusion systems. And these are some of the references, and I stop here. Thank you. Thanks for your.
It's a very common phenomenon. Thank you very much, Dr. Harsha. So from the audience side, do you have any questions? Because we have some time, like 5 minutes and so on, so we can discuss about the questions. Please feel free to unmute. Yes, sir.
Okay. Harsha, I have a couple of questions. Why do you assume the initial condition will be in C2 omega bar? All right.
No, that is not essential right now. We have just for the existence result, it's not essential that you are in C2 omega bar.
Okay.
Yeah.
I mean, another question.
Yes.
Yeah. So another question is, you see, if you add A, B, and 2C, then the right-hand side is going to be 0. So you have a conservation property. All right.
Let me go back. Yeah. Yes.
So I mean, does it help?
Yeah. I mean, you see, you're absolutely right. There are additional conservation properties, but how it helps to improve this decay rates, I'm not sure. Okay. This I have not actually thought about. Yeah, you're absolutely right. You can take various linear combinations of these equations to get additional conservations. Yes.
Okay, then
just one thought. But that may be hidden in the earlier ones that we already have. You see, it's like we are adding the two conservations and getting a new conservation. Right? Yeah. So it may not be a new conservation property.
You are doing 2.
Yes.
AC or B plus A. So it is hidden in that.
So yes, it is hidden in that, as you rightly pointed out. Sorry about this. Yeah. See, we are saying that A plus C is conserved, B plus C is conserved. So now if you add these two conservations, you will get A plus B plus 2C is conserved. Yeah. So it's just.
You see, essentially you have assumed that A, B, C, L infinity norm, both space and time, is bounded by some constant 1 plus t to the power some mu positive.
Yes.
Okay. Why
Could you
that is
repeat?
needed?
No, right. In fact, the reaction diffusion system, the degenerate reaction diffusion system that we have, it will have that property.
That you have
See,
proved. That is what I
yeah,
said.
that we have proved. I did not give the details. That we have proved actually. That the when dp is equal to 0 in the reaction diffusion system, the solutions actually satisfy that growth bounds, these growth bounds. The solution actually satisfies this. We are not sure whether the solutions to this degenerate system actually has a uniform in time L infinity estimate. That may not be true also. Because if your A, B, and C are uniformly bounded in L infinity, this is trivially the case, right? So our results help you recover what Develeth and Fellner did also. Because in their case, the non-degenerate case, the solutions are uniformly bounded in L infinity.
Okay.
In both space and time.
Yeah. Okay. Thank you.
Harsha, so thanks for this nice talk. I'm just curious to know, like, what kind of chemical reaction does give rise to this particular reaction model you have taken? Because is it like a second order reaction or something else? Because I have never encountered this kind of reaction term till now, so this is new to me. So I'm just curious.
So we are okay. So I don't have a precise, reaction in mind or anything. Okay, we are actually trying to study this one, but there are few papers which have studied related questions to this particular kind of three species models. There, I'm sure they have given some examples. I don't have the examples at hand.
Yeah, but this three species reaction A plus B goes to C generally doesn't have the C term individually on the right side. So I mean,
it may be disintegrating back to give A plus B. It may be a short-lived chemistry where these two react to give C, but C disintegrates itself to give back A and B. So there may be some such things.
Okay.
But
yeah, because
I don't have an example.
Even if you don't have the C on the right side, for example, in your reaction term, even if you don't have the C, the conservation properties you are trying to do, it's still going to work. Like A plus C is going to be conserved and B plus C is still going to be conserved. Because if you just drop the C term from all of them, then it still works.
So you are saying that there is...
Yeah, for example, if the C is missing from your right hand side, let's say, in all the three equations, the conservation still works, right?
No, but then, it will, the reaction term there is not coming out of any law of mass action if the C isn't present.
No, it does, because it says that if A plus B reacts and creates completely a new C and the A is completely gone, then you have the reaction term as A and B multiplied, which will be positive in the C equation and negative in the A and B equations. That's the standard second order reaction, which just creates a new product and A and B are missing.
Okay. Yeah. That way you can just drop the C's here, but somehow the coupling is lost. You have coupled only A and B in some sense, and because if you drop the C's, you want to drop the C's here, right?
C equations are coupled with both A and B, but A and B are not coupled with C. Yes, that's true.
Yeah. So you can solve them separately and then plug it in C and solve. Yeah. So that coupled nature will be gone. But I have not come across any, models where they have done this, what you're suggesting. Okay. No.
Yeah.
But
anyway,
you are absolutely right. If you usually in a typical reaction, some things are reacting to give something else, right? And it may not be just one. I mean, there may be two, at least two on the right side. Yes. So then you have to study models of this kind. But unfortunately, the global in time existence of solutions to these models, reaction diffusion models, are known only for quadratic nonlinearities, or maybe 2 plus something, 2 plus epsilon, when the powers are, at most 2. Yeah, that's the problem. The in general existence theory for these models is largely open. It's not known.
Thank you. I think Professor Pani was saying something. I stopped in between him. He was adding
No,
something.
that's fine. See, such models occurs in biological sciences. Yes, 3 species model. There are plenty of examples. Typical examples rather than. So such model really occurs in biological sciences under diffusion reaction models.
Okay. So next time I give a talk, I should add a example. Yes, I'll make sure.
Yeah. 3 species model, you can add it. It's interesting, but it's interesting to know that long time behavior, which the community in bioscience or biomathematics areas they study. Of course, they don't care about long time behavior, but they are using the large time behavior in their model. But as I understood now, there are some difficulties.
Yeah, and at least in this method, it is like we are mostly interested in getting explicit constants in all the decay estimates.
Interesting. Okay, thank you.
Yeah, thank you, sir. Is there any other question? Okay, then if there is no question, we can again thank you to Dr. Harsha for this wonderful explanation and the presentation. Thank you so much for your time, sir. And